Hello everyone, my name is Calvin Carpenter, and today I will be deriving the heat diffusion equation in both Cartesian and spherical coordinates. We're going to start off with the Cartesian version, and what we really want to understand about this equation is what energy is being stored in a set volume within the dimensions of dx, dy, and dz, as you can see on your screen in front of you. So starting off with the main equation that we're going to use, the most broad equation. It's going to be the energy being stored in that set volume equals the energy being generated in that volume plus the energy going in the surface minus the energy going out of the surface. And from this equation, we're going to basically break down every term and piece everything together, and it'll all make sense in the end. So starting off with the energy being stored, that's going to equal the density of that volume times the heat capacity times each dimension, dx, dy, and dz, times the change in temperature with respect to time. So when you break the energy storage equation into units, you end up getting kilograms per meters cubed for the density. For the heat capacity, you get joules per Kelvin times kilograms. And then for your dimensions, you get meters cubed. And for the dT, the change in temperature over change in time, you get kelvins per second. And when we cancel all of these units, so kilograms cancel, volume cancels, kelvins cancel, then you end up getting joules per second, or watts, which is the unit for energy in this. So the next term we're going to break down is the energy generation. So energy generation equals energy generation for that volume is the energy generation times each dimension. And when we break that down into units, we get joules per second times volume, and then we get the dimension for our dx, dy, dz. And then when you cancel units, you end up getting joules per second. Now we're going to look at the next terms, which are going to be the energy flowing in and the energy flowing out. So the energy flowing in is going to be the energy flow for x plus the energy flow for y plus the energy flow z. And I'll go ahead and label these diagram. So this is going to be our qx, qy, and qz. Now for the energy flowing out, we have the energy flow plus the distance that traveled. So in the x direction, it'll be the heat flow of x plus the distance it traveled. Same for y, same for z. And I'll go ahead and label that on the diagram as well. For the energy in, we're going to break down the heat flow of x, y, and z. And then for energy out, we're going to break down the heat flow of x plus the distance, heat flow of y plus the distance, and heat flow of z plus the distance. So for energy in, we can break down Qx into we can break down Qx into this. It's going to be the area times the heat flux, and that can be broken down further. And the area that heat flow in the x direction flows through is going to be the z and y plane. So it's going to be dz times dy for the area where the heat flow in the x direction flows through. So it's going to be dz dy times the thermal conductivity times the change in temperature over change in distance. And same applies for our heat flow in the y direction. It's going to be the area times the heat flux in the y direction, which is going to be the area in which the heat flows in the y direction is dz dx times the thermal conductivity times the change in temperature over the change in distance. And then for our heat flow in the z direction, it's going to be our area times the heat flux of z equals the plane of which the heat flow in the z direction flows through, which is going to be dx dy times the thermal conductivity times the change in temperature over change in distance. So that's the energy in values broken down. Now we're going to break down the energy out values. So the energy out values broken down can be broken down through a Taylor series, and that looks like this. It's going to be the heat flow in the x direction plus the partial differential of that heat flow in the x direction over the partial differential of x times dx. And same for the y and z. So I'm just going to write those out really fast. All right, so now we have enough information to write out our equation, plugging in our values. So our energy storage values that we found were the density times the heat capacity times dx, dy, dz times the change in temperature over change in time. And that was equal to the energy generation, which was that, plus, we're going to keep the energy in values as this for now. So we'll be able to simplify some things. And then the energy out was Qx partial differential of Qx over partial differential of x. Sorry, that's a minus there. And then minus heat flow of y minus the partial differential of heat flow of y over partial differential y minus heat flow of z minus the partial differential of the heat flow of z over partial differential of z. Sorry, I missed something. All of these have distance on the end. And keep in mind that these terms here, they cannot cancel because one's a partial differential and one's just a normal differential. So when looking at this equation, we can cancel a few things. So you'll notice that Qx and Qx cancel, Qy and Qy cancel, Qz and Qz cancel. And now we can plug in our values. Sorry. We're going to divide everything on each side by dx, dy, dz. And then we can plug in our values for Qx, Qy, and Qz with the area and the heat flux. We can plug those values into the partial differentials. So when we do that, we'll end up with the density times the heat capacity times change in temperature over change in time equals the energy generation, minus the partial differential of the heat flow in the x direction, which we solved to be dz dy times the thermal conductivity times that over the partial differential of x times dx. That's going to be multiplied by an area since we divided by dx, dy, and dz. So that's going to be multiplied by 1 over, that would cancel this too. So it's going to be 1 over dy dz. And then, so we're going to end up subtracting 3 terms. So it's going to be, the next one's going to be partial differential of dz dx times thermal conductivity times change in temperature over change in distance over the partial differential of the distance times area. And then the final term is the partial differential of dx dy times thermal conductivity times the change in temperature over the change in distance, the partial differential z times our area. All right, so now we're going to break down this equation further. So if you look here at this dz dy, these terms have no effect on the partial differential of x. So we can actually bring those terms out front of the differential. Same with these terms and same with these terms. And you'll also notice that when we bring those terms out, they will cancel with all of the areas. We can also bring out the thermal conductivity because in this instance, we're going to treat it as a constant, but that's not true for all scenarios because it just depends on the surface and the volume that you're working with. But for this instance, we're going to bring it out. So we're going to rewrite our equation here. So it's going to be the density times the heat capacity times change in temperature over change in time equals Q dot minus partial differential in terms of x times dt dx, and we ended up bringing k out front. So k is going to be out there, minus k times partial differential. Sorry, I just realized you can't see that. K times partial differential in terms of y. Dt over dy minus k times the partial differential of z times dt dz. So now we can do a few things with this equation. So here, and here, we can combine all of those partial derivatives to make second degree partial derivatives. And also, if we divide by our thermal conductivity, then we can do something with that. So first, let's combine our partial derivatives. So we have our density times our heat capacity times change in temperature over change in time equals all right. So now we can divide each of our terms by k, and we can get this. So we'll have our dt, change in temperature over change in time, times our density times our heat capacity over our thermal conductivity And that is going to be equal to, sorry, scroll down here. That's going to be equal to Q over K minus second degree partial derivative temperature in terms of X minus partial derivative of temperature in terms of Y minus the second degree partial derivative of temperature in terms of Z. And here, this term, right here, it's the inverse of the diffusivity constant. So we can replace that as well. So we have our change in temperature in terms of time times our inverse of diffusivity equals Q dot over K minus our second degree partial derivatives. Is our simplified version and final equation for the heat diffusion equation for Cartesian coordinates. All right, so now we're going to discuss the heat diffusion equation for spherical coordinates. A few things to go over before we dive deep into it. We're going to go over some of the dimensions for spherical coordinates. So obviously we have our x, our y, and our z, but now we have an r projecting outward. We have an angle theta between y and r, and then we have an angle phi, which is a projection between the length of r sine theta and the z direction. And so these values sorry, I just wanted to get rid of those highlights. These values will help us determine our volume dimensions and our heat flow values. So I'm just going to start off with QR. So QR is going to travel through this dimension, and it's gonna come out the other side as QR plus dr, traveling the distance of r, and then in the theta direction, it's going to travel the distance of theta and come out the other side as q theta plus d theta. And then for the phi direction, we're going to start off with q phi. It's going to travel through, travel d phi, and come out as that. So now we're gonna define the volume of this figure. So our differential volume is going to equal our dr times our r d theta times our r sine theta d phi. All right, so now that we have our volume defined, we can write out our equation. So as before, the energy stored equals the energy generated plus the energy flowing in minus the energy flowing out. And each of these terms can be broken down. The energy stored equals the density times the heat capacity times the volume, which is our dr, d theta, d phi times r squared sine theta. Our energy generation will be our energy generation through that volume times our volume, which is once again dr d theta d phi r squared sine theta. For our energy flowing in, we have QR plus Q theta plus Q phi, and then energy flowing out, we have QR plus dr plus the heat flow of theta plus the distance it traveled, and then plus heat flow in the phi direction plus the distance that it traveled. All right, now that we have broken every term down, we can define our heat going in and our heat going out values, our Q values. So we're going to start with the heat going out, actually. So our our Q R plus dr, so that's the heat flow plus the distance it traveled, is equal to, once again, it's going to be a Taylor series. So it can be heat flow in the r direction plus the partial differential of heat flow in the r direction over partial derivative of r times dr. And then for the theta direction, we've got heat flow theta plus the partial derivative of the heat flow for theta over partial derivative of theta times d theta. Finally, we have our phi values equal heat flow in the phi direction plus the partial derivative of the heat flow in the phi direction over the partial derivative of phi times d phi. And that's our terms for the heat going out. And then for, here, let me just label that. Then for heat going in, we have, this one's going to be a little bit different. So we have the same type of equation as we did for Cartesian, but we're going to have to add a few things in for some of the coordinates. So we have area times our heat flux for R is equal to, our area was dr, sorry, it was dr d theta d phi times r squared sine theta. No, sorry, that's our volume. My bad. Just erase that real quick. Our area for this is going to be the plane in which the heat flow in the r direction travels through. So that plane is going to be r d theta r squared, sorry, d theta d phi r squared sine theta times our heat flux, which is going to be our thermal conductivity, which once again we're going to treat it as a constant, times the change in temperature over the change in distance. For our next term, our Q theta equal to our area times the heat flux of theta, which is equal to the plane. The area is going to be the plane in which the heat flows through in the theta direction, which is r sine theta d phi times dr. Sorry, let me make sure I got that right. dr d phi r sine theta. Yes. Okay. Times our thermal conductivity. And then this term is going to be a little bit different because our thermal conductivity is in terms of joules per meter times second times Kelvin. So our value on the bottom needs to be in terms of length so that we can end up with joules per second for energy. So we can't just write d theta out here. We need to quantify theta as a length instead of an angle. So we're just going to use the length used in our volume, so it's going to be r d theta. And then for q phi, our heat flow in the phi direction is going to be area times heat flux in the phi direction equals the area of the plane in which the heat flows in the phi direction, which is going to be dr d phi times r. No, that's wrong. Dr d theta times r. Times our thermal conductivity times change in temperature. And then once again, we have to quantify d phi as a length so that our thermal conductivity can cancel. So we're going to have to use r sine theta d phi. So we have our values for the heat flowing in and the heat flowing out. So now I'm going to plug everything back into our main equation, and things are going to cancel out, and we're going to do the same division that we did with Cartesian coordinates, because the same concept applies here. So starting with our energy storage, so we have our density times our specific heat times dr, d theta, d phi times r squared sine theta equals our energy generation, which is q dot dr d theta d phi r squared sine theta equals, plus, we're just going to leave these terms as qr plus q theta plus q phi. And then we're going to subtract our energy out, which is minus qr minus partial derivative of qr over partial derivative of r times dr minus q theta minus partial derivative of the heat flow of theta in terms of theta times d theta. And then we're going to subtract one more term. That'd be our phi. So now that we have it written out, you'll see a lot of things will cancel again. So we'll have our qr, q theta, and q phi all cancel. And now we'll do the, sorry, wait, I messed that up. Sorry, here. Oh, I really forgot a lot here. Actually, wait. No, I didn't mess that up. Sorry. Okay, now we're just going to rewrite our equation, so it'll be a little bit easier to work with. So our density times our heat capacity times dr d theta d phi times r squared sine of theta equals our heat generation in that area times dr d theta d phi times r squared sine theta minus partial derivative of the heat flow in the r direction in terms of r times dr minus partial derivative of the heat flow of theta in terms of theta times d theta minus partial derivative of the heat flow of phi in terms of phi times d phi. So now we can plug in our values for our heat flow of r, heat flow of theta, and heat flow of phi. of phi into our equation. So that'll look something like this. Scroll down a little bit. So we will have our density times our specific heat times dr. I just realized I didn't have a d up there. d theta d phi times r squared sine theta equals q dot times dr d theta d phi times r squared sine theta. And then this term's going to be a little bit long. So we're going to subtract partial derivative of QR, which is going to be d theta d phi r squared sine theta times k times dt over dr. I'm just going to do this. And then minus our partial derivative in terms of theta times dr d phi r sine theta times our thermal conductivity times dt over r d theta. So it can be in terms of length. And then one more term to subtract. We'll have partial derivative in terms of phi times dr d theta times r times k, our thermal conductivity, times dt over r sine theta d phi. Actually, I forgot these terms have dr, d theta, d phi on the end. So now that we've done that, we can divide this volume, divide that volume through, and that's pretty much the same thing as last time. So each of our coefficients here will be able to be taken out, and then we'll divide. Also, the k is being taken out. Forgot about that. Now that should clean things up a bit. Next step that we're going to do is divide by that volume and cancel out terms. So let's just write this out. The volumes. This is going to be a long one. So we have our density times our specific heat times dr d theta d phi times r squared sine theta equals our heat generation in the volume times dr d theta d phi r squared sine theta Now we subtract. We're just rewriting all of this with, actually, I should do this then. Sorry. All right, when we divide out our volume, we will be left with this. So we've got our first term, which is our partial derivative in terms of the radius, which is d theta d phi r squared sine theta times the thermal conductivity times the change in temperature in terms of the radius. And then we have on the outside, when we divide by volume, we are left, when we take out dr, we're left with d theta d phi r squared sine theta. And then next we have the theta term, which is dr d phi r sine theta times the thermal conductivity times the change in temperature over r d theta. And then when we divide by the volume, that term turns into dr d phi r squared sine theta. And then for the final term, partial derivative in terms of phi, we have dr d theta, sorry, that's phi, dr d theta r times our thermal conductivity times the change in temperature in terms of r sine theta d phi. And then when we multiply, we'll divide by the volume, we get 1 over dr d theta r squared sine theta. So that's a lot, but we can cancel some things. I just realized that my energy storage was incorrect from the beginning. So I'm just gonna add this in there. This is all multiplied by the change in temperature in terms of time. So we're gonna have to go through and add all that. So this is multiplied by change in temperature in terms of time. And then all right, that should be good. Okay, now we can cancel. So Looking at this first term, it's in terms of r, so we can pull everything out that doesn't have to do with r. So we can pull out a sine theta, and that will cancel. We can pull out d phi and d theta, leaving us with, here, let's just rewrite so we can add on to this. Density times our specific heat times our change in temperature in terms of time equals our heat generation for that volume minus the partial derivative in terms of r times r squared. Oh, also we can pull k out of the terms. So we'll have r squared times the change in temperature over the change in radius times k. Times k over r squared, I believe. Yeah. And then looking at the theta term, we can cancel dr, d theta, sorry, dr, d phi. We can't cancel that sine theta, but we can cancel this r right here, leaving us with the partial derivative in terms of theta times sine of theta times the change in temperature in terms of theta and then outside we have k over r squared sine theta. And for our last term, we can cancel dr, d theta, and we can cancel an r down here. And then we're left with this. Partial derivative in terms of phi times change in temperature over d phi. What's left on the outside is k over r squared sine squared theta. Just making sure everything looks right here, and it does. So now we're able to divide by k and create our thermal diffusivity inverse constant. I just realized that that this cut off a little bit. Sorry about that. I'll let you see the whole thing. But now we can divide by our k and or our thermal conductivity and replace it with our inverse of our thermal diffusivity constant. So let's do that real quick. So our density times our specific heat over k times the change in temperature over change in time equals u dot over thermal conductivity minus partial derivative in terms of r times r squared, change in temperature in terms of radius, times 1 over r squared minus partial derivative in terms of theta times sine theta times the change in temperature in terms of theta times 1 over r squared sine theta. And then our last term minus our partial derivative in terms of phi. Sorry, that can be merged. So our second degree partial derivative of t in terms of phi times 1 over r squared sine squared theta. And so this value right here, that can be broke down into 1 over our thermal diffusivity constant. So let's just rewrite that real quick. Rewrite this whole thing. So our density, no, not density. Okay, so 1 over thermal diffusivity constant times change in temperature in terms of time equals our energy generation for that volume over our thermal conductivity minus our partial derivative in terms of r times r squared times change in time in terms of radius times 1 over r squared minus partial differential in terms of theta times sine theta. Has to stay in there because there's theta in the partial differential, times the change in temperature over change in theta times 1 over r squared sine theta minus our second degree partial differential of temperature over phi times our 1 over r squared sine squared theta. And that, my friends, is the solved version of the heat diffusion equation for spherical coordinates. All right. Thanks for watching.